In this lecture, we will be discussing Newton's divided difference interpolation, or better say Newton's interpolation. But before starting this topic, let me remind you what we read in last class. Suppose we are given this much n data points, so we can always have a polynomial of degree n minus 1 which passes through all these points. And equation of such a polynomial can be rewritten in this format, or we can rewrite it as this e naught x minus x1 into x minus x2, like in this format only. So what I wish to say is, to represent one polynomial, we can have several methods, we can have several ways we can rewrite it as, and this is all about interpolation here. So in this case, how we write our polynomial as, suppose we are given any function fx, and the corresponding interpolating polynomial, that is my Pn fx, and how we represent it as, suppose it passes through my data points, that is x0, f0, x1, y1, and correspondingly up to xn, yn. So how we represent it as, my first term, that is some c0 plus x minus x0 into c1 plus x minus x0 into x minus x1, and obviously c to this side, and in similar way up to n terms. And my last term, that would be x minus x0 into x minus x1, and this will go on up to x minus xn minus 1, and this will be corresponding coefficient, that is my Cn. So this is my polynomial, and what are the condition given to us? That this polynomial of mine, this passes through this point x0, f0, and if this passes through this point, that means f0, this will be equal to c0 plus this term. So when we will put x is equal to x0, obviously this term will vanish, and correspondingly all higher terms, this will vanish to 0. So this means that c0, this is my f0, and applying the second condition, that is when x is equal to x1, the corresponding value of f, that is f1. This means f1, this is equal to c0 plus x1 minus x0 into c1, plus when we'll put x is equal to x1, this term will vanish, and if this term will vanish, that simply means the correspondingly all higher terms will vanish, because all higher term that will contain x minus x1, so this will be 0 again, and this means c1, that will be equal to f1 minus c0 upon x1 minus x0, and the value of c0 is nothing but f0, so we can write it as f1 minus f0 upon x1 minus x0, right? And let me rewrite it as, see, this interpolation, this is all about rewriting, how you rewrite terms as. So this will be equal to f0 upon x0 minus x1 plus f1 upon x1 minus x0. And if you can observe that these two terms are symmetric terms, right? And let me represent it as sum f x0 x1. Okay, now let me change the pen color. Okay, now the third term, that is when x is equal to x2, the value of corresponding value of f is f2. So this will be c0 plus x1 minus x0 into c1 plus x2, actually x2 here, x2 minus x0 into x2 minus x1, and this will be c2, and obviously the higher terms that will vanish to 0. So from here what we can write is this c2, I have to extract the value of c2 as we know the value of c0 and value of c1. So this will be equal to f2 minus f0 minus x2 minus x0 into f of x0 x1. So I replace this value f1 minus f0 upon x1 minus x0 with this value. Okay, so let me move the slider. So this will be this upon this term, that is x2 minus x0 into x2 minus x1. So what you can do is you can take this term common and rewrite this as f2 minus f0 minus x2 minus x0 into f of, that is my x0 comma x1. Okay, and when you will expand this term, what you will get is f2 upon x2 minus x0 into x2 minus x1 plus f1 upon, okay, well you can guess here, this will be x1 minus x0 into x1 minus x2, and third term that you might have thought, this will be equal to x0 minus x1 into x0 minus x2. This is again symmetric, right? And we can write this as, or represent this as f of x0 comma x1 comma x2. So in a similar way, we can prove using induction that Cn, this term will be f of x0 comma x1 up to this section. And how we will calculate this? Using this formula only, right? So now let me replace the coefficient. Actually what we are doing is we are trying to find out the coefficient C0, C1, C2. So my polynomial Pn of x, this will be equal to C0, and that was nothing but f0 plus C1. C1, that is my f of x0 comma x1 into x minus x0 plus f of x0 comma x1 comma x2 into x minus x0 into x minus x1. And similarly in this way, this will continue up to f of x0 comma x1 comma x2 up to this terms, that is xn minus 1. What we are doing is simply replacing this coefficient of minus with what we got, right? So here actually this will go up to xn, right? So this will be actually be xn, and here this will be x minus x0 into x minus x1, and this terms up to x minus xn minus 1. So this is my general interpolating polynomial, and what we need here is a linear approximation or a linear interpolating polynomial. That is my p1 of x. So this will be equal to f0 plus f x0 comma x1 into x minus x0, and this is nothing but f0 plus this is f1 minus f0 upon x1 minus x0, and this multiplied by x1 minus x minus x0. So this is the formula for my linear Newton's interpolation, right? Write this as, this is nothing but f of x0, that is my first term, plus f of x1, that is my second term, minus f of x0 upon x1 minus x0, and this multiplied by x minus x0. So you can observe here, this is a polynomial of degree 1. Yeah, degree 1, that is the power of x, that is 1 only. And now we'll move on to our next topic, that is calculation of error bound or calculating error. What will be maximum error and what will be the exact error at any point. And for that, what we'll do is we'll define a function. Okay, first of all, let me define the error function. Error function that will be this fx minus pn of x. So pn in case of linear, that will be equal to 1 only, and the value of n. And error, see here, the fx is my actual equation, and pn, this is my polynomial what we interpolated, what we approximated. Like if you remember, if fx is equal to sine x, we do have a Taylor series for this, that is x minus x cube upon 3 factorial, and so on. So this is my fx and this is my px, right? So to calculate this error, what we do is we assume a polynomial of our own which satisfies some properties. What properties? Okay, let me make it so. Suppose you are considering my polynomial as this f of t minus p of t and thus minus fx minus px into t minus x naught into t minus x1 upon x minus x naught into x minus x1. So what you can observe from here is whenever you will put t is equal to x naught, just put t is equal to x naught. So this will be f of x naught minus p of x naught. And whenever you will put t is equal to x naught, so this term will vanish. That simply means this whole term will be 0. And if you remember that at this 2 point x is equal to x naught and x is equal to x1, f of x and p of x, they are equal. Or basically we calculated p of x considering these 2 points only. So at t is equal to x naught, g of t, this will be equal to 0, right? And at t is equal to x1, that is my second point, again this term will vanish and this will be equal to f of x1 minus p of t1, and again this will be 0. So this g of t or g of x1 simply, this will again be 0. And at one more point, that is my t is equal to x, just simply put t is equal to x here. So whenever you will put t is equal to x, so this will be x minus x naught and this term will be x minus x1. So the numerator and denominator both are equal. That simply means this will converge, or that simply means this will be equal to 1. And again this will be fx minus px minus fx minus px. So again this term will vanish. That is g of t, this will be equal to 0. So what we are getting is for three values of x, that is x0, x and x1, we are having the value of function gt is equal to 0. And if you remember class 12th or 11th of yours, you may have read one theorem, that was your Rolle's theorem. What it says is, if for two values of x, that is a and b, that is in this particular interval, if f of a, this is equal to f of b is equal to 0, then there must exist c lying in this interval such that f dash of c, this is equal to 0. So we will be having two values, let's say a1 and a2, for which this g dash of a1, this will be equal to 0, and g dash of a2, this will be equal to 0. And what we will do is we'll apply the same logic here, that is for this two value a1 and a2, right? For this value a of a1 and a2, we are having g dash of t is equal to 0. Then again applying Rolle's theorem, we will be having a value, let's say a, such that f g dash of t derivative, this is equal to 0, or we can simply write as g dash of t is equal to 0 for some value of t which is equal to a, right? So what we'll do now is we'll differentiate this equation of Mainz. Okay, so let me copy this equation here, just wait for a while. Okay, so this equation of Mainz is selected. Well, there's a problem. Do is we will differentiate this equation of Mainz, and this will be equal to g dash of t, and g dash of t, that will be f dash of t minus p dash of t, and here this side, like this term will be treated as constant fx minus px, and this term also. So what we will be left with is minus fx minus px upon x minus x naught into x minus x1, and when we will differentiate this term, so you will get 2t minus x naught plus x1. We'll again differentiate this, So g double dash of t, that will be equal to f double dash of t minus p double dash of t, and this term is a constant, so this will vanish and you will be left with 2 only. So this will be equal to minus 2 times f of x minus p of x upon x minus x naught into x minus x1, right? As we know that this pt, this is a linear interpolated polynomial. That simply means the degree of this polynomial is 1. This will be something like plus b. When you will differentiate this 1 times this p dash of t, this will be equal to a, and when you will twice differentiate it, this will vanish to 0. That simply means this term is 0, right? So we are left with this only, g double dash of t, this is equal to f double dash of t minus this term. And the logic that will be used is, we do have value t is equal to a, for which g double dash of t, this is equal to 0. That simply means f putting value of t is equal to a, this term will be 0, and that simply means this f double dash of a minus this term, this will be equal to 0. So moving this to my left hand side, this will be equal to f double dash of a is equal to 2 times f of a minus p of a upon here, this will be equal to f of x, not f of a, because we are putting the value of t is equal to a, not x is equal to a. X here is treated as constant. So this will be 2 times fx minus px upon x minus x naught into x minus x1, right? And this fx minus px, this term is nothing but my error term that we defined as e of x. So this means that we can write our error term e of x, which is fx minus px, as x minus x naught into x minus x1 upon 2 times f double dash of a, right? And if you remember, this is the same error term what we calculated in the Lagrange linear interpolation, right? Also, this value of a is lying in between x1 and x0. So as to maximize my error term, or to find the bound of this error term, we have to maximize this term. And for this, what we have to do is, we have to maximize this value of derivative, that is f double dash of a. So we will take the maxima of f double dash of a such that this condition holds, that is my x lies in between x1 and x0. So this will be my maximum error, and suppose you have to find the corresponding value of x where this error will be maximized. So what we do is, we change this term with some constant term. Let me assume that the maxima of this derivative f double dash of x is some m. So what we'll do is, we'll find the derivative of this error term. So this will be equal to 2x minus x naught plus x1, and this constant term, that is m by 2. And if you remember, to maximize any polynomial, what we do is we differentiate it and equate it to 0 so that we get the extrema of it. So when we equate this with x is equal to e dash of x is equal to 0, we'll find the value of x as x naught plus x1 by 2, and replacing the value of x with x naught plus x1 by 2, and this error term, what we'll get is error term, or you can say the maxima of error term, the maximum value, this is equal to x naught plus x1 by 2 minus x naught into x naught plus x1 by 2 minus x1 into maximum of f double dash of a by 2. And when you will calculate this, you will get it as x naught minus x1 whole square upon, sorry, this will be equal to x naught minus x1 whole square upon 8 into maximum of the second derivative. So this is the maximum error what we can have in any case. So this was all about Newton's interpolation, how we derived interpolation, Newton's interpolation formula, and how we derived the error term, right? Okay, you might be thinking that how we will find the maximum value of f double dash of a. even the maxima will exist or not. Suppose your function is sin x, derivative of this is cos x, and derivative of this cos x, this is again minus sin x. So you can always have a limit to this function, that this will lie in between minus 1 to 1. Obviously the maximum value that is equal to 1. So this was all about today's lecture, Newton's interpolation and error. Thank you so much. Stay tuned.